All right. Hello again, everybody. It's me. You know who I am. If you've seen a couple other videos, I'm gonna start this video with a disclaimer. The content of this video is gonna be based off this paper, scaling data-driven robotics with reward sketching and batch reinforcement learning. But for this video, we're actually just gonna be focusing only on reward sketching. That's really the only purpose for this. And I've given this disclaimer in other videos, but I showed my videos to a few people that I know, and they all told me the same thing, like, these aren't tutorials. And I'd like to let you guys know that these are not tutorials. Like I've said in almost every single video, these are code walkthroughs. You should not be coming to these videos as like a first step. This should be one of the last steps. Like if you've read a paper or you've gone over a topic, but you don't know how it might work out in code, this is the video for you, just to see how one person decided to implement it. Maybe you're having difficulty and understanding exactly what it would look like in code. You don't even know where to start. You could get an idea from my videos, but it's not like and you guys, if you've seen the other videos, you know that I don't go super deep. I kind of explain it. Here's why I did it like this in the code. Here's this thing from the paper or from this topic. Here's what it looks like in code. Next step. None of this stuff is supposed to be used specifically in your own code. In other videos, they always talk about like, oh, and you just copy and paste this into your own project and you'll be up and running. With a lot of these things, especially since there's so many different papers, you have to take like select parts, and fitting all the parts together could be difficult. So don't expect to just copy code directly and paste it in and everything's going to be running. You need to do things for your own, whatever it is you're doing. Anyways, let's talk about reward sketching, exactly what's going on, and the parts of this paper we're going to cover. I tried to do this in TensorFlow at first, had some issues, and then I tried to do it in pytorch, had some issues. I got it to run, but it's not the same as the paper. It's by no means the same as the paper. I'll discuss what's going on, what's different as we go through it. So essentially what this paper is doing is we have an agent or a human operator or like some autonomous agent, and it does some actions through an environment, and we have a series of states. So we have a trajectory, which is just a series of states, and we actually don't need the actions for these. We're just going to be holding on to the states that the agent goes through or demonstrator goes through. And then we're going to take those demonstrations, those trajectories, and we're going to give that to a human to label them and say, oh, this, these states that they were in, they were doing very well, and the goal is to lift something. So they were doing that very well in this part, but this part they were doing very poorly. And you'll give it a scalar reward of any value from 0 to 100, and you can rescale it to whatever you want. That's just the values that I'm going with. So you just label each value, oh, it's doing it very well, 99 out of 100, or whatever. It's doing very poor, 10 out of 100. And then we use those values with the loss function to update the parameters of a neural network. And then what we have is there's this thing called never-ending storage, which is essentially just a replay buffer or some type of data storage for all of our trajectories. So our new learned reward, it's going to label, it could label, I don't do that. It could label all the past trajectories. So let's say past trajectories were, they had reward estimates for each individual state. You train your reward model a couple more times, and now it's more up to date. Now it's better at estimating rewards. So you say, I have this entire never-ending storage of data of all these trajectories that have labeled rewards, but they're not using the most up-to-date reward function. So you could use the same reward function to go back and relabel the data. So that's the biggest takeaway from all of this. And obviously, you could do the last steps where it's just taking some type of RL agent and sampling from this never-ending storage so it can do its own updates and whatever. And if you were going to do that, you'd obviously want to hold on to things like actions and like log probs and everything else. But right now, the only reason we're using it is to update the reward model. And in the future, you could just have any agent holding on to its own trajectories, and the only thing it has to be concerned about is it receiving the correct reward. And if you modeled, if you're doing the correct reward shaping through this method, then you can expect the environment will be giving it the correct reward. Okay. So we're gonna skip everything. I just gave you like the basics of it. They did it for like agent, and right here, like this would be 0 and this would be 100, and like this green area, there's a certain threshold whether you can consider a single frame successful or unsuccessful, and that's one of the metrics that you're trying to optimize. Does it label the successful frames as successful and the unsuccessful frames as unsuccessful, and things of that nature. So the agent acts randomly. Then people are given like this thing, and you can draw into it and you can label it. Like things are so they call that a reward sketch. So like this is someone sketching this. Oh, very low reward here, very high reward here, very successful. Oh, it's doing better. Oh, whatever. And then you take all these sketches and you take those and use that to update your reward function. And they taught it to do some cool things like normal pick and place tasks and inserting a USB, which is cool. If you look at the video, like they totally brutalized, like it looks like it's a white port, but that's just because the USB hit it so many times. Obviously, like it had to learn, but you can see like had to gather a lot of experience for sure. Okay. And let's go ahead and look at, so we're going to skip this because it's assuming we're also updating the agent at the same time. We're not doing that, like I said. So we're going to update our reward function, and then within our environment, a separate environment that you're training your agent in, you can just pull this reward function, load it into the code over there, and use it to reinforce that agent over there. Like we're just going to assume these are entirely different, just for the sake of simplicity. So yeah, let's go over the basics of reward sketching. We just have a combined two-term loss, and we're going to talk about how we get there in just a second. So so the sketches for an episode or a trajectory is consider that sketch of x of t for all time steps inside of that trajectory. So we're going to go ahead, and for every single time step inside a trajectory, we're going to sketch a reward. So we're going to label a value between 0 and 100 for every single step in the trajectory. Okay. Okay. And sketching is particularly suited for tasks where humans are able to compare two time steps reliably. So you can, so if you're looking at the thing, you could say this, it's doing poorly here and it's doing better over here. So that I'm going to assign lower reward here and higher reward here, which is a little bit similar to reward preferences, but obviously it's a different loss. And we'll talk about how you can use these sketches to actually update the other model from reward sketches. Okay. So any one individual frame, we're going to call, so we have a neural network, and well, that's going to be our reward function, and it's going to be parameterized by, what is that? Psi. Okay, so it's parameterized by psi, and so let's say now we have a labeled reward sketch. So let's talk about the update rule. So what we're gonna have to do is, for an entire trajectory, which is labeled, that we call that a reward sketch, and we're gonna go ahead and we're gonna sample 2 individual frames from this reward sketch. So assume we have a labeled trajectory, and they're labeled of rewards of, this time step was doing good, this time step was doing bad, etc., etc., etc. So we're going to go ahead and sample 2 frames from our reward trajectory called x of t and x of q, well, x sub t, x sub q from the same episode. And let's actually talk about why they set up the loss like this by looking actually at this other paragraph that I just skipped. So that although there's high agreement between annotators of the relative quality of time steps within an episode, annotators are often not consistent in the overall scale of the sketch rewards. We therefore adopt an intra-episode ranking approach to learn reward functions rather than trying to regress the sketched values directly. So what they're essentially saying is, if I say, oh, this should get 70 reward per se, instead of just training the model to say, oh, when you see the state, give it 70 reward, they figure out a different way to do it. And the reason for that is because, let's say I think it's doing well, so I say, oh, it's doing pretty well, 70. Someone else might say it's doing pretty well, 60. And someone else might say it's doing pretty well, 99. However, let's say that there's the expectation for all 3 of those people that it's doing well. There could also be, if they're looking at 3 separate frames, and they think it's doing poorly, someone could say, this is doing poorly, I'll give it 10. I'll give this one 20 because it's doing poorly. I'll give this one 5 because it's doing poorly. So the thing is, people are not consistent with the values that they'll give to it. However, the poor ones will be, lower than the high ones. Like relative to each other, if they're showing a good frame and a bad frame, they'll give the low frame a lower reward, high frame higher reward. Okay. So that's the reason that they chose the loss that they did. So let's go ahead and read through this entire paragraph and then look at what it looks like mathematically, and then we can look at it in code. Okay. So specifically given two frames, x sub t and x sub q, in the same episode, we trained the reward model to satisfy two conditions. First, if frame x sub t is successful or unsuccessful according to the sketch s of x sub t, it should be successful or unsuccessful according to the estimated reward function parameterized by psi, which is r sub psi of x sub t. The successful and unsuccessful frames in the reward sketches are defined by exceeding or not a threshold tau of s, which is tau of whether or not it's successful, and the unsuccessful frames in the predicted reward exceed or not a threshold tau of r sub 1 and tau of r sub 2. Okay, and you'll see these in the loss in just a second. So this is just saying, was it successful or not? And so the second loss that we have is if if the sketch of x sub t is higher than the sketch of x sub q by a threshold mu of s, then the reward of x sub t should be higher than the reward of x sub q by a threshold mu of r. So this second term is just saying if the sketch says that it's that x sub q is 20 higher than x sub t, then the reward should also say that it's also at least 10 higher. Like if it's saying there's a gap in between this high frame and this low frame, according to the sketch, the reward function should also estimate that there should be a gap. Maybe not necessarily of the same size, but it should say, yeah, like this one is higher than this one by 30. The estimate should also be higher by 15 or something. So it's enforcing like a bound or an interval, well, a bound between them, saying like, got to keep the distance. Remember, highs are high and lows are low. So you're trying to enforce that. Yeah. And so let's look at what these look like in the beginning. Let's talk about the terms very quick before we look at this right here. So we have a rank loss and we have a success loss. So here's the value. So mu sub s is equal to 0.2. So if this, so essentially if the sketch says there's a bound of at least 0.2, so that's what we need to say, and there also needs to be a bound for the reward estimate, which is 0.1. So we're essentially saying if the sketch says that they're at least 0.2 apart, the reward should say they're at least 0.1 apart. Okay. There's tau of s, tau sub s is equal to 0.85. Tau r1 is 0.9. Tau of r2 is 0.7, and lambda is equal to 10. And the reason that we have a lambda is because it's much more important to successfully and unsuccessfully rank the frames for this paper than it is to label the frames as successful or unsuccessful than to enforce the boundary, because the loss for the success is 10 times greater than the loss for the rank, which is, we get that from our lambda. So let's look at these terms and what happens in each case, and then we're going to go ahead, throw this into the code, and we'll be done super quick, hopefully. Okay, so let's look at our rank for a loss. So the rank for the loss is assuming we have two terms sampled from the same trajectory. Okay, so we have two states, sorry. So we have the sketch of x sub q and x sub t, and so assuming x sub q is greater than x sub t, so if xq minus xt is greater than mu of s, where is it? Mu of s is greater. So essentially, if x of q is greater than x of t by 0.2, then what we're going to try to do is we're going to try to enforce that the reward of x of t minus x of q is also greater than mu of r. And the way that we do that is we take the maximum value over this between 0 and this other term. And let's talk about what happens between these terms. So if we have this bound that is greater than mu of s, and we have mu of r right there as well. So if x sub t minus, if the reward estimate of x of t minus the reward estimate of x of q plus mu of r, so if the, let me see. Let me read, I don't want to say anything too incorrect. I mean, obviously not everything's perfectly correct. Okay, so if the reward estimate is already, if it's already saying, yeah, you know, the values between x of t and x of r are already greater than mu of r, then this is going to be negative. So we'll have this term right here on the right. This value will be negative, and the maximum between 0 and this term will be 0 if it's negative. So what this is saying is if it's already enforcing this rank loss, so if it's already saying, yeah, the sketch says that there's a difference of this much, and the reward also says that there's an estimate of this much, that means that this value will be negative. So the max between 0 and a negative value will be 0. So it's saying it already is estimating that there's that difference in between. So this value is going to end up being 0. So we don't need to optimize for this because we're already saying, hey, like, let's enforce this boundary. And the reward function is enforcing that boundary by a distance of mu of r. So everything's good. We don't need to optimize. However, if that is not the case, if the reward of x of t minus the reward of x of q plus mu of r, if this boundary is not greater than mu of r, or this distance is not greater than mu of r, this term will end up being positive. So then we're gonna, our rank loss is gonna be the maximum between a 0 value and a positive value. Okay, so that's gonna be a positive loss. So it's gonna say, you know, we're expecting a distance of at least 0.1 in between them, and the reward is not estimating that the distance between them is greater than 0.1, so we need to have a loss. So since this is a positive value, the greater value between 0 and a positive value is going to be positive value. So we end up with an actual loss for the rank. Okay, that's how we end up with L rank, or L rank loss. Okay, now let's look at our loss for a success condition. Okay, and so this, okay, so I forgot to mention, we're assuming x of q is going to be greater than x of t. And if they're the same value, this is also going to be 0. So if they're not, if like they're equivalent values, like it kind of disregards it for us. Okay, so let's look at the success loss for psi, which is a reward function. So assuming that this is a successful frame, okay, so let's go ahead and assume that this is a successful state or sketch of the state or whatever. So the sketch says this is a successful frame because the sketch of x is greater than tau of s, and tau of s is our success criterion, or criteria, whatever you want to say. So which is 0.85. So we're saying, oh, the sketch for this frame says it was successful because it got because the sketch was greater than 0.85. Okay, let's go ahead and so the success would be the maximum between 0 and tau sub r1 minus the reward estimate of the actual frame. So let's talk about what happens in this condition. All right, so okay, so for this term, if it's successful, so if it's the sketch says it's successful, okay, and okay, so I'm having trouble reading my notes, But let's just go through this together. Let's figure this out together. So if tau of R1 is 0.9, okay, and our reward estimate minus, so if tau of R1 minus the reward estimate for a state is, so essentially, I guess the correct way to say this is if the reward estimate is saying also the same thing that is being said on the outside. So if the sketch says the sketch of X, of frame X, is greater than the success condition, then the reward for that should also say it is greater than the success condition. If that is not the case, then this term will end up being negative. Sorry. So if that is the case, this term will end up being negative. So the max between 0 and a negative value will be 0. So if it's doing what it's supposed to do, so if the reward sketch is saying, yeah, this is, the sketch said it's successful, we also think it's successful, this term on the right is going to be a negative value. So there's going to be no loss for it because the max between 0 and a negative is going to be 0. Okay? And we're going to do the exact same thing, but this, and we're just adding these two terms. And I ended up doing it personally as a conditional. Okay? But essentially we're saying, so if the sketch says that we're not successful, so if the value of the sketch is less than the success value, which is tau of S, we get the same thing. So if the reward estimate says it's also less than tau of R2, so we're saying if the sketch estimates that it's if the sketch determines that it's not successful and the reward determines that it's not successful, this value will be according to R2 for the reward estimate. This value will be negative, and the maximum between a 0 and a negative value will be 0. So we're saying, well, the sketch said it's unsuccessful, and the reward said it's unsuccessful, so we're negative, and the max is 0, so there's no loss. However, let's say the reward sketch determines that it's successful. We say, okay, it determines that it's greater than 0.9 for some reason. So its estimate of it was like 0.95 or something. So 0.95 minus tau of R2, which is 0.7, is going to be a positive value. That would be 0.25. So since it was incorrect, we have a positive value. The max between 0 and 0.25 is obviously 0.25. Okay, and that would be the amount of loss for the success for this. And the way that I did it was in my own code. So going over this, the first step I had to do was determine for so you sample 2 frames from a trajectory, and you have it set up so x sub q is greater than x sub t. And once you do that, you can use the rank loss, okay, as long as it fits this condition right here. And then what you can do is you can also do the success condition. And the success condition, the way you're doing the math is you're only technically for any one frame, you're only using one of these two, okay? Because one of them is assuming that the frame was sketched successful, or one of them, one is assuming the sketch was for that frame was successful, and the other is assuming the sketch for that frame is unsuccessful, and it can only be one of the two. So you can have an if statement, and that will determine which formula you're going to use, or equation or whatever, for your success condition. Okay, let's go ahead, jump into the code, and let's hope this goes well. Okay, so might be a lot longer than I had initially anticipated. Okay, so let's go ahead and get our magic going. So I'm just doing this in Colab. So we need our magic, %sign matplotlib inline, our imports from matplotlib, import pyplot as plt, from ipython.display, import clear output. This is just so we can make things look nice as we're doing our reward sketches, and you'll see how we do the sketches. And import random, import numpy as np, import time, and import statistics. Okay. And then we need to define our environment. This is just a simple grid world. Okay. You guys can just copy this code from here. I don't want to go into it. And this is slightly different than the other grid worlds. I have the x's as the first two and the y's as the last two instead of x, y, x, y as it was previously. But you can see that here, just the way that I've assigned it. And that, you know, that's our state. Our state is equal to that grid. So, you know, self.state is equal to, you know, call that function on it. And we have our step. So we're not going to be giving rewards. Like I said, we're just going to be collecting trajectories of states. So we just, our step function just takes an action that our agent has done and it modifies the state because it only needs to modify the state. So this is just utility, you know, if it's, you know, 0 through 3 for our north, east, south, and west on our 2D plane. And, you know, if the action is 0, you know, change the y's to move it up. If it's 1, change the x of our player to move to the right, or to move down if it's south, or move to the left if it's to the west. Okay, so let's go ahead and talk about gather experience, which is just a simple function. So we're just going to be using a random agent to collect experience, and we're going to be labeling that random agent. Obviously, if you want to gather experience educatedly, or whatever the word was, shouldn't use that word. I don't think it's a word. If you want to gather experience, your best thing to do is to have an agent collecting the experience and to learn. So as it gathers more experience, it can give you better rewards to sketch. But now we're just gonna, since we're gonna be running it for only a single trajectory, that doesn't really matter too much. But obviously, instead of using a random agent, you'd want an actual agent that has been learning that you'd like to use. So we have a function called define gather experience that takes an environment, and it has experience as just an empty list, and it wants to know what the episode length is going to be, so it can run the environment for that many steps. We initialize the environment, and then for a number of steps inside of the episode length. So for I in range episode length, sample an action, random action on the range 0 through 3, tell it to step through there. So say environment, hey, here's your new action, and we're gonna go ahead and take the state from our environment by calling input.state, turn that into a NumPy array, and we're gonna append that to our experience. So we're gonna, at the end, when this loop is done, we're gonna have our experience trajectory of length 13 with 13 different states in it, and we're gonna return that experience to whoever called this. Okay, let's talk about sketching the rewards. So in the paper, they you know, it's a bunch of people working on it, and they were able to make like this great little online tool, it looked like, where you can, or program, I guess, where you can label each individual frame. But what I did was, just for the sake of simplicity for this tutorial, it's not really about how you sketch them, it's about the losses. Like I've said before, it's all about the losses. So what I did was, we have an entire trajectory segment, and we're just going to partition that into you know, segments, and we're going to label each segment. So let's say there was like 50 frames, and we partitioned it into like segments of length 4. We're going to have it's called 12 different segments, and each segment will have a reward value for that, but it'll be for like not just for one individual frame, but it'll be for like a frame and like the 3 frames around it, kind of thing. Which is just, it's just easier for us to do that because of like the way we're collecting input, and so we don't have to build a tool to collect that, and that's something you could build on your own time. Okay, so let's go ahead and talk about how, once we have gathered experience, we can sketch our rewards. So to sketch our rewards, we need to have our experience that we gathered from an agent or some random policy or something. So we're going to have a trajectory segment, which is empty, an annotated trajectory, which is going to be what we're going to return, which is empty in the beginning, number of plays. And so we're going to play like each segment from the trajectory multiple times, so they can look, so the user can look at it multiple times, and then they can rate it. So you want them to look at the segment multiple times beforehand, just so they make sure they understand what they're seeing, yada, yada, yada. Okay. So for I in range, the length of gathered experience, so for the entire trajectory, we're going to make a trajectory segment. And what we're gonna do is for iron range length, we're pretty much gonna go ahead and slice our entire gathered experience, and we're gonna make a trajectory segment from that gathered experience. Okay, so trajectory segment dot appends gathered experience I. Okay, so let's go ahead, and so we have once we actually have the length of the trajectory segment is equal to 4, so we're going to be doing it in like little segments of length 4. We're going to go ahead and play that for the user. So we're going to say, hey, we're uploading a segment. Now we have a segment of length 4. Now we're going to let the user use that segment. And right here at the bottom, you'll see for every time we're in the loop, we hit the trajectory segment, so it's empty again. So once we collect a sketch for a four frame period, we're going to reinitialize the trajectory segment so we could do the next 4 frames inside of the gathered experience, from the gathered experience. Okay, so this is all right here just to go ahead and display the code. We're making a tiny little animation, like it's a pretty poor animation of our grid world, and we have our player and our goal in the grid world, and we're just watching our player navigate the grid world through there. So we just let it know, hey, start of clip, time.sleep, just so they have a second, and clear output. And this is just because we're doing it inside of Colab, so we need a way to clear our output between frames. So it's not putting frames underneath each other, it's looking more movie-like ish-esque, whatever. So for all of our frames in the trajectory segment, just take the X's, take the Y's, let the user know, hey, like this is what you're going to be ranking it off of. So, it's go to goal. Set your axis limits and graph it. We're going to use a scatter plot, and we have plt.pause as 0.4, plt.show, clear output. And this is just for the actual animation part. It's not an animation. So once they see this animation play for them a couple times, we're going to say, hey, what reward do you want to give this clip? So we're going to get the user's input for reward, and we're going to say 0 through 1. I'm going to say 0 through 100 divided by 100, which will end up giving you a value of 0 through 1 for the actual rewards. So we're going to turn that into a float and put that in reward. And we're going to say, hey, like now we have a trajectory segment and a labeled reward for it. So let's label this trajectory segment and put that into our new annotated trajectory segment so we can return that. So for time step and trajectory segment, add it to our annotated trajectory, the specific time frame, and the reward that was given to that trajectory segment. And we reset the trajectory segment so it's empty so we can collect the next frames. And we finally return that annotated trajectory. Okay. And then, so these are just the definitions up here. So we need to start doing that. So we need to go ahead and gather experience. So we call gather experience on our environment, which was already initialized at the top right here. Environment is equal to, you can move that around if you like, I guess, definitions up top, then actually calling some things down here. So create our environment, we call gather experience on our environment, and it returns experience to us. Okay. And then we call sketch rewards, and we're going to have annotated trajectory afterward. And I'll play it right now, but you can see that each one of these is an individual time step, and you see every 4 of them have the same, and so we have time step, and each time step has the state associated with it and the reward for that state. And you see that the rewards go in groups of 4 because we show it based off of 4. And you could label each individual state as you want. If you want to build a tool and label each individual state, you can do that. This is just a tutorial to help you guys get running. So I didn't spend the time to do that. Okay. And so now let's talk about our reward model that's going to be learning and the losses for it. Okay. So this is all just to collect the data and label the data, to annotate our trajectories, or to sketch our rewards for our trajectories, everything up until this point. Then we have to define our model, which we're about to do, and then we have to define our loss and run everything. So I'm gonna do our import. So import torch from torch, import neural network at, import NN. And this is just if you want to use GPUs, you need a device. Otherwise, it's going to be CPU, and we don't need that. That was copied directly from pytorch, as you can see right there. And look, still got some pytorch stuff in there. Just copy the model for up and running in pytorch, kind of their quick start. So we define a model called rewarder, inherits from neural network. Several layers. I don't think we need that flattened layer, actually. And what we do, and we just make sure that the output just has a single value, because it's just returning a scalar, an estimate of the state, of the reward of the state. And our forward pass, it just goes ahead and it takes our observation, which is the state, and we get a reward and we return that to user. So let's go ahead and instantiate that model, call it model. So our model, I'm just going to delete that. So did that twice. Okay, so our model is going to be equal to rewarder, and we need an optimizer. We're just going to go ahead and use classic stochastic gradient descent. And it's going to be optimizing the model parameters, and the learning rate is 0.003, or 1e to the -3. Okay, so that's scientific notation for you guys. Okay, now let's look at the update rule. This is literally the last block of code, and it's not pretty. Okay, so we had inside the paper, we had some, some variables that we need to declare at the beginning. So we have our success condition, which is mu of s, which is 0.2. Mu of r, which is not success condition. Sorry, the distance. To determine if they're a certain distance, if they're greater than 0.2. Also, we want the reward to determine that they're a distance of 0.1. So mu of r, mu of s. Our actual success condition for success loss, which is tau of s, which is if we sketch that the frame is greater or less than this, that's what's going to determine whether we use this or this, because it's determining whether it's successful or unsuccessful, and then that determines what operations we do to it. All of this is just running operations, just running a bunch of operations. Okay, we have tau of r1, which is 0.9. So we're saying if the sketch says it's 0.85, we want to make sure that the reward really enforces the sketch. So we want to make sure that it's not even greater than 0.85. We want to make sure it's greater than 0.9. And the same thing for R2. So we're saying if the sketch is saying it's less than 0.85, we don't want it to say it's less than 0.85. We want it to say it's less than 0.7. So we really are trying to create that boundary. So higher rewards get higher sketch states get higher reward estimates, and lower sketch states have lower reward estimates. And they're essentially creating a boundary in the middle and trying to enforce that boundary just to make everything happen. And we have a lambda of 10, so that our success, the loss for the success is 10 times greater than the loss for the rank, or how much it contributes to the total loss. Okay, so we go ahead and we defined all those terms up there. Gonna delete that. Average loss. So they don't talk about number of updates, but so assume you have a trajectory. You don't want to just sample 2 frames from the trajectory, because you have an entire labeled sketched trajectory. You don't want to just sample 2 frames, xt and xq, and do a single update from that. What you want to do is, if you have an entire trajectory, you can sample several times and do the updates on that. So that's obviously, I'm assuming the way that they did it, they probably had, I have no clue how they did it, but they had this all as one huge update step. I couldn't get that going. Okay, I'm just implementing the rules. Okay. So instead of saying we're going to just take the whole trajectory, we're just going to be sampling individual xt and xq. So how many times are we going to do those samples? We're going to do that, let's say, 50 times. Let's just say we have super long trajectories. We're just going to sample 50 times, do 50 update steps for it. So we're going to go ahead and we gathered our experience earlier, but what you do is you'd pull an annotated trajectory from your never-ending storage, as you see in the paper. But we're just assuming we don't have never-ending storage, that our annotated trajectory that we just labeled and we pulled right now for this one update step that we're going to do, let's just assume we pull that from never-ending storage. Okay, so we now have an annotated trajectory that's pulled from never-ending storage. So we have to make sure that x sub q is greater than x sub t. So this is just sample from our annotated trajectory, two different states, and we're going to check and remember each two separate time steps, and each time step has a state and then a reward. So we're making sure that the reward, if the reward for A is less than the reward for B, then x of q is greater than is equal to B, and x sub t is equal to A. And this is just to enforce that x of q is greater than x sub A. Okay? So then we say we have two time steps now that we've sampled, and so if they're the same, it will just fall within the else as well. Okay. And like our losses will be 0 if they're the same as well. Okay. So we're just gonna put them in time steps for our second update rule, because for a second update, so assuming we have two time steps, you'll only update this once. But the way that I did it, I'm just checking for each one whether it falls into this category or this category. So you have to iterate over every single time step to do this success loss. Okay. And you guys are not going to like the way that you guys are seeing it. If you stick around this long and you're about to see how it looks, you're not going to like it. Okay. So so we have our first update rule, which is to enforce the rank. Okay. So we need x sub q, x sub t, and the predicted values for x sub t, and x sub q, and these predicted values get by running x sub q and x sub t on the actual reward model. Okay. So what happens is this is just where we're saying if the reward for x sub q minus the reward for x sub t is greater than mu of s, then our loss is going to be equal to the estimated reward of x sub t minus the estimated reward of x sub q plus mu of r. Like I said, and if it's already doing what it's supposed to be, this term is going to be below 0. Let's see. Yeah, and this term is going to be below 0. Otherwise, we're just going to have it equal 0 if it's, okay? So let's go ahead. We call model.train so we can train our model. We make our estimates for x of t, x of q by passing it each individual state, okay? And then we calculate our rank loss by giving it our original xq, xt, and the predictions for xq and xt. So, you know, this can return a negative value right here. So we're just making sure if it is a negative value, don't forget, we're actually just going to be 0. So we're actually not going to do the optimization step for it. And what I did was I optimized each step differently. So I optimized for the first term, then I optimized for the second term, which is why like consider these as like 2 optimization steps. Although it should be 1, I did it as 2. Okay? And I'll show you the TensorFlow code for it in a second, how it was supposed to look and how it actually looked when I started in pytorch. But I was having some issues, so I had to break it down into 2 separate update steps because it was giving me issues. Even in TensorFlow, it was as 2 different, but it looks better. I'll just let you see it. So if you'd like to try to implement it in TensorFlow, you know, depending on whether you're using pytorch or TensorFlow, maybe you could get an idea for it. Okay. Anyways, so if it's not less than 0, that means our loss is a positive value. So we're going to call our optimizer.0gradients. Going to call backward on our loss, and we're going to tell our optimizer to step, so that will update our model parameters. Okay. Okay, and now let's look at our second loss, which is our success loss, okay, which we get from right here, the loss for success. I showed you the TensorFlow by accident. Whoops. So we have our two time steps, x sub q, x sub t. So we're gonna now update for each simple each one. So whether you see a condition right here, whether the time steps reward is greater than tau of s, or the time steps so if the time steps reward is greater than tau of s, so we're saying if it's been sketched as a successful frame, we're going to get our success loss via this, which is via this. Otherwise, if we sketch it as unsuccessful, so the reward is less than tau of s, we're going to use this to calculate our success loss, which we get via this right here. And you see here that they're added together. I'm just doing it as conditionals. If there's a huge issue with that, someone please let me know, because it looks the same to me. This is obviously not optimal, because adding the terms together would be I mean, I guess it'd definitely be a lot cleaner for sure, but don't really see much else. So depending on whether we sketch it as successful or unsuccessful, we're just going to apply either one of these formulas. So if we sketch it as successful, it's tau of tau sub r1 minus the reward of the state times lambda. And if we sketch it as unsuccessful, the loss is equal to the reward estimate of the state minus tau of r2 times lambda. And then now we have a success loss for our second update step. So we're saying as long as, and these could still be negative values, and we got to call the max over those. So we're just going to say if max between 0 and the success loss. So if it's less than 0, we can assume that it's not going to be the max. So we're saying if the success loss is greater than 0, to do an update step. Otherwise, we don't need to do update step because the loss is going to be 0, so there's going to be no update. Okay. So if the success loss is greater than 0, we're going to call the same thing with the last one, optimizer.zeroGradients, success loss.backward, optimizer.step, and then we're going to go ahead and print the combined loss for both of them for each update step that we run. And that's it. And then you can go ahead and use that to, so you now have like an updated reward function. And if you'd like, you could go ahead and use that to relabel all the data in your never-ending storage, or you could call this update step multiple times and sample different annotated trajectories. And obviously, I didn't even do this as a loop. You'll see that it's a loop in just a second, just so we can run a bunch of update steps on it to see that it's learning. But otherwise, everything is based on the implementation of how you're using it, what your storage looks like, all that. So we're going to run through this all at once. Factory reset runtime, run all, and it's going to go ahead. Our random policy is going to gather experience, and it's going to put that into the trajectory. Oh, it's going to play it for us. So here's our goal, and it looks like it's going to the left. So that should be very low reward. Out of 100, I'm going to give that a 10 for those 4 frames, because we have our goal in the upper right, and we saw that we had our player. And it kind of moved left, right, and left, and so it wasn't really doing anything, so we're going to give it a low reward, okay? And so that kind of looked like it was staying in place. I'm going to give that also a low reward of 20. It wasn't really doing much beneficial. It's not going to the goal, so let's look. So it looks like it's staying in the same place. So I'm going to give that like 0, but it's not collecting it right now. For some reason, let me go ahead and rerun that. It should be, everything was working. I ran it like just a few minutes before I started this. Sure, everything was fine. So this is actually a sketching the reward. So start of clip. So we see it moving up to the left, the player. And we have our goal down there. So it's not really doing what we like, so we're going to give it a low reward. Again, so let me do 15. Okay. So it's kind of moving back and forth to the left. I'm going to give that 30. Pretty bad, but it's staying in place. Oh, it moved to the right and down. All right. That's a little bit more preferable. I like that a little bit more. So I'm going to give that, it's not success, but I'd say I'm going to give that 95. Just because, you know, compared to the other ones, it's not doing well. So we have our annotated trajectory right here. And we'll go back to that in a second. And we run 50 update steps on it. So from this entire annotated trajectory, we're going to sample 2 frames randomly. Okay. And one's going to be x of t, one's going to be x of q, and it's going to make sure that x of q is greater than x of t. And then it's going to do our 2 update steps on them. So we saw in the beginning, the loss was kind of high, 1.1, 0.7, 0.6, 0.5, 0.4, 0.24, 0.35, 0.31, and you see our loss is steadily decreasing, and to a very low value. So this is, it seems like it's overfit, but well, my assumption is actually that it's overfit. And there's several times where you see that like there's a loss of 0, just based on the frames that it sampled or whatever. But you can't, obviously you can see that there's learning. Like when the loss goes from 1.19 to 0.76 to 0.73 all the way down to like 0.2, that's how we know it's been learning. So we can see that a reward function has been learning, and you can go ahead and save that. And you can pull, once you've saved your reward model, you can go ahead and pull that into a separate environment that you've built. Maybe it's a similar environment, and this might be the environment that your actual agent is collecting data off of. So when it gets rewarded by this separate environment that has this specific reward model that has been fit to whatever it is you'd like it to do, the agent will be very well informed because it's being rewarded based on what you've taught the reward model to do. I hope this was helpful. Like I said, this is not, you know, these are not the best tutorials. I understand that. But if you've read the paper already and you're like, I don't really know how it's supposed to go, here's a first step to it. Try to get both of these steps. So try to like what you should try to do is combine these 2 into a single step, and then let's assume this is a single step, you combine the update rule, the first one and the second one, or the second and the first, and you just add them together. Let me just show you what it looks like in Colab. Everything in Colab is the same, even labeling. So we do our imports slightly different, importing from TensorFlow, importing layers, defining the actual reward model, but it has a single output. That's all the same. Initial instantiating it. That's all the same. The only difference that comes is the actual update steps. So you can just take a look at it. I'm just going to talk through it for like 30 seconds. You know, within the scope of gradient tape. We're going to call it on our data. We're going to have our estimates of our rewards, and then we're going to go ahead and call max between 0 and the actual term, which is the reward of x of t minus the reward of x of q plus mu of r, which reward of x of t minus reward of x of q plus mu of r. And then we have this other term down here for success for a second update rule. Whoops, wrong one. So then we're going to optimize. Okay, and we're going to do the same thing for our second update rule, but for state and states, because we have our 2 states and states. We're going to call our reward function on those states. Depending on whether or not you know, the sketch is determining it's successful or not, we'll do this update rule or this update rule, depending on whether it's sketch is successful or unsuccessful. And then we're just taking the max between 0 and, if it's successful, tau of R1 minus the reward of the state times lambda. And if it was sketch is unsuccessful, the loss will be the max between 0 and the reward of the state minus tau of R2 times lambda optimize. And that's everything. If you can get it in TensorFlow, let me know. Or if you can get it in PyTorch, where it looks a lot more like the TensorFlow one versus what I did, let me know. Send me an email. You know, I'd love to see your code. I'd like to know how I can possibly do this better. I know it doesn't look neat by any means, but what I can assure you is this update rule is the same update rule that you see right here. So if you want to optimize your reward function via means of reward sketching. This right here is the same as this. Whoops. All of this. And everything we have our first and second update rule. The way they're implemented is slightly different. Oh, what I did want to mention before I finish this is that if you consider this, just bear with me. So we talked about human preferences, and we did that in the last one, but we only did it for single states instead of the summary of a trajectory for multiple states. But the great thing is that we would have like human annotators label this. I like this trajectory more, and I like this trajectory more. So we actually had human annotators do that. Human annotators view between these 4 states and these 4 states as the ones on the right as being more preferable, because the sum of the rewards for these 4 and the sum of rewards for these 4 over here are different, and the one on the right is greater. And you can do that just, I mean, there's different ways you can pull that from your own information. And obviously, these 4 are greater than these 4, etc., etc. So you have like a already fixed length trajectories where you can compare to, and you already have them compared. So you could just, you could randomly, let's say you have a ton of sample annotated trajectories. You can go ahead and randomly sample sequences of length 4 or 8 or whatever value you want from those annotated trajectories. And you'll have 2, and you'll already have them with reward sketches on them. So you already know which one's preferable. So you can take those 2. So you sample two segments from each annotated trajectory, and you take the sum of the rewards for each of them, and you already know which one is preferred. So you feed those to your model for the reward preferences, obviously summing over them this time because you'll have a full trajectory, and you just do your loss on the other one the same way. But the great thing is that if you when you're sketching the rewards, the annotated rewards, the rewards that are the trajectories that are sketched, they're labeled for you, like as which ones are more preferred by the user. So you now have trajectory segments where some are preferred and some are less preferred. Just find out which ones they are, and feed that to your reward preferences model. Hopefully that made sense. Anyways, hope this was by some means useful to someone in some way. It was really just to show that, that I'm slightly competent with code. Hopefully someone will hire me at some point. If you like this video, give it a like. It really helps out because, the more views that this gets, more likely it is that, it looks better on my resume. So anyways, we're recording for 58 minutes. Oh, less than an hour. That's great. So you guys all have a nice one. Thank you for watching. Like, comment, subscribe. Contact me if you guys need anything or about this kind of stuff or suggestions, things of that nature. Have a nice one. Take care.